Henderson-Hasselbalch is an incredibly useful equation for dealing with pHs in a solution that has a buffer, right? So it takes into account the equilibrium reaction that's there. Henderson-Hasselbalch equation is pH is equal to pKa plus the log of the conjugate base concentration over the weak acid concentration. So this part of my Henderson-Hasselbalch equation takes into account where in the buffering system we are, right? Am I right at the middle? Am I toward the beginning? Am I toward the end? What are my relative concentrations of my product and my reactant? The pKa takes into account the equilibrium reaction that I have there at my system, and then this is my pH, right? So it's a great way of being able to make sense of the titrations that we have. So if I'm looking at a titration curve where this is my pH, this is my volume of base added, there are two inflection points. The first inflection point is going to be at my titration point, my end point, where I have no buffer left. This is where you have that steep curve up, it's halfway up, or it's the change where I have the concavity of my curve changing from this to this, right? Halfway to that point, volume of base added, will be where my midpoint is. And the midpoint is also another inflection point where I have a change in the concavity of my curve going from here to this kind of curve. So this green part is where my buffer is present. The initial point is where I haven't even started anything. All I have is my weak acid. And my end point is where I have no buffer left. So this green region is basically where you're going to be using the Henderson-Hasselbalch equation in order to figure out what the pH of your system is. At the initial and at my end point, I'm not going to be using Henderson-Hasselbalch. So if I'm looking at this qualitatively, initially when I have no base added, really all I'm looking at is how much of my acid has dissociated. That depends on my Ka value. And so all of my pH is just going to be dependent on my Ka value. So the lower my Ka value, the higher my hydrogen ion concentration, the lower my hydrogen ion concentration, and so my pH won't be as low. Again, the lower my Ka, the less of this has dissociated, so my hydrogen ion concentration will be lower, and so my pH won't be as strongly affected. As my base is added, I have this Le Chatelier's principle that kicks in, where what starts to happen is as I add hydroxide ions, I'm removing the hydrogen ions, and what I'm leaving behind are the conjugate bases. And so my conjugate base ion concentration increases while my weak acid concentration decreases as Le Chatelier's principle kicks in, right? So as I'm adding hydroxide ions, my system shifts to the right, which means that my weak acid concentration goes down and my conjugate base concentration goes up to compensate. So the way that we look at this is that we first assume that moles of hydroxide ions that are added are used up, and they use up the hydrogen ions completely. And then I find the new HA and my A minus, my weak acid and conjugate base concentrations, and then I use it into my Henderson-Hasselbalch equation to compensate for that shift right. One thing at midpoint, the moles of base added equal half the moles of acid present, so half of my weak acid has been converted into my conjugate base. At that point, the log of this is going to be equal to 0, so my pH is equal to pKa. So this is also a really important way of being able to figure out what my Ka of my acid is from a titration curve. So if I look at it and I know that this is my midpoint, right? This is where I have my change in concavity. That midpoint, that pH is going to be equal to my pKa. And if I take my pKa, 10 to the negative pKa, I can find out what the Ka of my acid is. So all of those Ka and Kb tables were derived experimentally, again at certain temperatures, from the titration curves from which they were derived. So this is why titration can be so important. It gives us a sense of what kind of acid we have, what the Ka is, what the Kb is, and then we have a sense of how it behaves. Now we're going to look at what the Henderson-Hasselbalch equation used with numbers. So we're going to look at it at 5 different points. The important thing to remember is that because stoichiometry deals with moles and we're adding solutions together, we're going to briefly just convert everything to moles and then back into the concentration after we have a final total volume, because Henderson-Hasselbalch uses concentration. So it seems a little complicated, but the more that we get into it, it'll be a little bit, hopefully, more enlightening. So we're going to do a sample titration of a weak acid with a strong base. I'm taking 25 milliliters of a 0.3 molar solution of hydrofluoric acid, and I'm adding to that the same concentration, so 0.3 molar solution of sodium hydroxide. The Ka of HF is equal to 6.6 times 10 to the negative 4. And we're going to look at this at 5 different points. The initial point where the no base is added, before the midpoint, after the midpoint, between the midpoint and the end point, and at the end point. So we'll find out that at the initial and the end point, all I'm going to use is ice with Ka or Kb. Everything in between, we're going to use Henderson-Hasselbalch. And while we're using everything in between, right, so steps 2, 3, and 4, we're going to use, instead of ice, something called SRFC, which is pretty much ice, but it's just looking at the moles first. So S, R, and F kind of correspond to I, C, and E. It's the starting, the reacting, and the final, but with moles. And then the C is just a reminder to convert everything into concentration before I convert it plug it into my Henderson-Hasselbalch equation. So by using SRFC instead of ice, it's just that extra reminder that I have to use moles first and then finally convert to concentration at the end. So first point, haven't added any base. I just want to know what my pH of my acid is. So I have a 0.3 molar solution of hydrofluoric acid. My Ka is small enough from my initial concentration, so I can pretty much apply the 5% rule. For our intents and purposes, it will work. So 0.3, I'm just going to say the initial is equal to my equilibrium for my hydrofluoric acid. I'm starting out here. It's dissociating equally, so my concentrations of both my hydrogen ion and my F- ion will both be X. Here's my Ka expression. Hydrogen ion times fluoride ion over HF is equal to 6.6 times 10 to the negative 4, which was my Ka. So when I solve for X, I'm solving for my H plus ion concentration. So here's the derivation. My H plus ion concentration is equal to 1.4 times 10 to the negative second molar. The pH is the negative log of that, so it ends up being at 1.86. So I'm looking back at my original titration curve. My initial value here will be 1.86. If I add 10 milliliters of my 0.3 molar solution of sodium hydroxide, my sodium hydroxide is a strong base. So however much I add, that's however many moles per liter of my hydroxide ions I'm going to have. A little bit of things here. I'm not going to convert milliliters to liters. I just have to remember that milliliters times molarity gives me millimoles. That's fine. And millimoles divided by milliliters gets me back to molarity. So I'm just going to convert, just multiply my volume times my molarity and just pretend that it's all, moles and moles per liter. So I start out with 25 milliliters of a 0.3 molar solution of my HF, and that's 7.5 millimoles. 25 times 0.3 is 7.5 millimoles. And I'm adding 10 milliliters of a 0.3 molar solution of NaOH, so I'm adding 3 millimoles of hydroxide ion concentrations. Don't have anything yet. I'm going to assume that all of my hydroxide ions are reacting completely, so they will pull off 3 millimoles of hydrogen ions from HF. So in the end, finally, I will have 4.5 millimoles of HF and 3 millimoles of fluoride ions. Nothing here because it's reacting completely. Then I have to convert to concentration because that's what my Henderson-Hasselbalch uses. So I added 25 milliliters and 10 milliliters. So these 4.5 millimoles of hydrofluoric acid are going to be now over a total of 35, or 25 plus 10 milliliters, which gives me a molarity of 0.1287 molarity. So it went down from 0.3 to 0.1287. And my fluoride ion concentration is going to be 3 millimoles over 35, again 25 plus 10, and it ends up being 0.0857 millimolar. So as we said before, as I'm adding base, my weak acid concentration goes down 0.3 to 0.1287, and my conjugate base concentration goes up from 0, and in this case to 0.0857. I now plug it into my Henderson-Hasselbalch. So pKa is the negative log of my Ka. My Ka was 6.6 times 10 to the negative fourth, so the negative log of that is 3.18. So my pH is equal to 3.18 plus the log of my conjugate base over my weak acid concentration. So 0.0857 over 0.1287 is equal to 0.666. So the log of that is equal to negative 0.1766. If I add that to 3.18, my pH is at 3. So at the beginning, my pH was 1.86. My pH is climbing, but it's not climbing as fast as it would if I didn't have that buffering system. At the midpoint, in this example, both my hydrofluoric acid and my sodium hydroxide are both at 0.3 molar. I did that just to make my life easier. So half the volume of acid is going to be the volume of base needed to reach the midpoint. So I have 25 milliliters of acid in here, so I need to add 12.5 milliliters of my base. So 7.5 millimoles, 3.75. Now at this point, after they've reacted, I'm going to end up with 3.75 millimoles of HF, 3.75 millimoles of fluoride ions. So at the midpoint, by definition, the moles of conjugate base will equal the moles of my weak acid. Because the moles are equal, it doesn't matter how much I have, they're all in the same vessel, my concentrations will all be equal. So because my concentrations are equal, the log of this, right, this is going to be equal to that. That means that my ratio is going to be equal to 1. The log of 1 is equal to 0. So my pH equals my pKa, which we said before. So it's now 3.18. So if you see, I added, right, I went from adding 10 milliliters to now 12.5 milliliters, which is not that much, but I only started with 25. My pH only went from 3 to 3.18. So my pH is really just inching up. Now if I'm looking at the point between the midpoint and the end point, so I'm adding 20 milliliters of my 0.3 molar solution of NaOH, SRFC again. 7.5 is what I started out with, millimoles. Now I'm adding 20 times 0.3 or 6 millimoles of hydroxide ions. I have nothing here. Assume that it reacts completely, so -6, +6. So I'm ending up finally with 1.5 millimoles of hydrogen fluoride and 6 millimoles of fluoride ions. I put that over the total volume, which is now 25 plus 20, so 25 is what I started out with. So 1.5 over 25 plus 20 is equal to 0.0333. I'm like losing my HA, which we knew was going to happen. And now as I'm increasing the amount of fluoride ions, it's 6 over 25.2, 25 plus 20, or 0.1333 moles per liter. The log of that, so 0.1333 over 0.0333 is equal to 4. So the log of 4 is equal to 0.602. Now I'm adding that to the pKa, so my pH is 3.78. So remember that adding 25 milliliters is what will get me to my end point. I've already added 4/5 of the way up to end point, and my pH has only gone up to 3.78. Right? So 1.86, it then went to 3, 3.18, now 3.78. I'm really just inching toward that. It seems like I'm not going to get to my equivalence point. We are now right around here, right? So this is where when I started to add it here, this was at my midpoint. This was after my midpoint. I'm right here. And now I'm expecting my pH to shoot up. So at my equivalence point, I'm going to first assume that all of my hydrogen fluoride reacts with my NaOH, right? All of it's gone. And I create 7.5 millimoles of fluoride ions in a 50 milliliter solution. Why 50 milliliters? Because I started out with 25. They have the same concentration, so that means I have to add 25 milliliters of my base in order for it to be titrated. Remember, equal moles because of my balanced equation. And if I started out with 7.5 millimoles of HA ions, HA, then I'm going to convert that completely into my conjugate base, which will be 7.5 millimoles of fluoride ions. So at the end, I have 7.5 millimoles of fluoride ions, nothing of HF, nothing of sodium hydroxide. So basically what I have is a system in which I have my fluoride ions in with water. It's acting as just a base. So F minus 7.5 millimoles over 50 milliliters is my initial concentration of my F minus ions. F minus is a base, and so it's the conjugate base of HF, so I have to use Kb. I know that my Kb is equal to Kw divided by Ka. So Kw is 10 to the negative 14th. My Ka was 6.6 times 10 to the negative 4th. So my Kb for F minus at 25 degrees Celsius will be 1.5 times 10 to the negative 11th. Now I have absolutely no problem using 5%, right? Because 0.15 is many, many times greater than 1.5 times 10 to the negative 11th. So definitely can use the 5% rule. So I do icebox. I have nothing else except for I'm dumping in an anion into water. So this is my reaction. I'm assuming the 5% rule, so 0.15 will carry through. I had no HF or hydroxide ions, and now I'm going to create that. My Kb expression will be HF times OH minus over F minus equals 1.5 times 10 to the negative 11th. X is equal to, and this is important to remember, X is equal to OH minus ion concentration. So when I find that, which is 1.49 times 10 to the negative 6th, I take the POH if I'm taking the negative log, and that gives me 5.82. And then I have to remember that the pH is 14 minus that, so my pH is 8.18. So simply by adding 5 more milliliters, right? Because remember that 4.4 was when I added 20 milliliters of my NaOH. Here I'm just adding 5 more milliliters to get to the titration point. At the point where I was 5 milliliters away from my end point, 4/5 of the way there, my pH was 3.86. And then all of a sudden that last 5 milliliters shoots me up to 8.18 as my pH. So this right here would be 8.18. So again, it also helps reaffirm the idea that when I'm adding a strong base to a weak acid, at the titration point, my pH will be greater than 7 because I'm going to have excess hydroxide ions there. So Henderson-Hasselbalch is a great way of quantifying what we already understand about the relationship between weak acids and bases and buffering systems that are in equilibrium.